Hello, geometry students. We are continuing on with our discussions on similarity, and today we're going to apply some of the lessons we've learned on similarity to what happens with triangles. Okay, so let's get started. Our objective for this lesson will be the student will apply triangle similarity postulates to tell if pairs of triangles are similar or not. Okay, I'm recording this lesson in advance. Okay, I predict that this will be the lesson for Thursday, November the 14th, but don't hold me to that. Okay, but copy down your objective. Tentatively, this will be Thursday, November the 14th. As always, press pause anytime you need more time to copy something down, and then hit play when you are ready to move on. Okay. Now, a lot of the discussion that we're getting ready to get into is going to feel and sound very familiar, at least it should, because we had some of this same discussion when we were talking about congruent triangles last Friday. Okay, so you don't necessarily need to copy this part of it down. I'll tell you when you can tune back in and keep on copying. But just like with many other topics in geometry, triangles are of special interest when it comes to studying similar polygons. This is because triangles carry certain properties with them that will allow us to predict their similarity based only on select pieces of information. That's exactly the same as we did with congruent triangles. Now, the postulates we're going to look at today can greatly cut down on the amount of work that is required in order to say the two triangles are similar or not. We just have to take what information is given and compare it to the postulates to see if one will work or not. Okay, so tune back in. Let's start copying some stuff down now. All right, the first postulate that we're going to look at is called the angle-angle similarity postulate. Now, just like with the congruent triangles, you're going to find that the names of these postulates, they're going to tell you exactly what it is that they're looking for and what order they're looking for it in. So obviously, angle-angle is saying that if we have two angles from one triangle congruent to two angles of a second triangle, then the triangles will be similar. Okay, now obviously that means we would be thinking about using this postulate if all we had in the triangles was angle information. And it's possible you might have some other information mixed in with it, but obviously we're saying predominantly we have angle information. Okay, so this will enable us to make the prediction of triangles being similar without having to go through any of the proportions for any of the side lengths for that triangle or those triangles. Okay, so a possible example, a generic example might look like this. Okay, we have two triangles. Obviously, we have two angles that are congruent. We can tell that by the angle congruency marks there. And if you can find that in a situation where you have two triangles, where you got two angles that are congruent from one triangle to the other, then we would be able to establish that, yes, triangle ABC is similar to triangle DEF by angle-angle. And yes, you can continue to abbreviate these with A's and S's rather than having to write out the angle word and the side word. Okay. Keep in mind when you go to identify your triangles as being similar, you can name the first triangle with its vertices in any order that you want. The ABC, we could have put it in any order that we wanted, but however we establish the order naming the first one, we got to name the second one in exactly the same order. In this case, that would be D and E and F. Okay, we have another similarity postulate, and this one should sound very familiar. It is the side-side-side similarity theorem. Now, first off, just a little side note on theorem. Okay, it says theorem instead of postulate. Remember that a theorem is a big, elaborate math rule that has to be proven in order to be true. In other words, it's not common sense. It doesn't seem like it ought to work that way. Okay, but it does. A postulate is more of a common sense type statement that doesn't really require a lot of proof. Okay, so that's the difference between a theorem and a proof, or a theorem and a postulate. Okay, but you should be wondering, where have you heard the side, side, side before? This was also one of the rules that could prove two triangles to be congruent. To prove two triangles congruent, we wanted the three sets of sides to be congruent to each other, but with similarity, we're only concerned about them being proportional. So it says that if the three sides of one triangle are proportional to the three sides of a second triangle, then the triangles are going to be similar. Okay, so obviously we would be thinking about the possibility of using the side-side-side similarity theorem if we knew all of the side lengths in a pair of triangles, but maybe we're short on some of the angle measurements for the triangles. Now, this one doesn't save us a whole lot of time or energy, but it is a shortcut in the sense that we don't actually have to be able to prove the angle measurements in order to be able to get the similar, establish that two triangles are similar. Okay, but getting that your three three sets of side lengths have to be proportional, well, this is where all the work on similarity comes into play anyway, setting up the three different proportions according to what corresponds to what, and then, of course, cross-multiplying in those proportions, proving that the proportions are actually going to be equal to each other. Okay, so again, this one doesn't cut down on a lot of work, but it does give us an out if we happen to not know much about the angles in the problem. Okay, and once you can prove that your three sets of proportions are true, then you can say, yes, I have two triangles that are similar. Triangle ABC is similar to triangle DEF, and this one would be by the side-side-side similarity theorem. And yes, you can abbreviate SSS for side-side-side. Okay. Now there is only one more rule that goes along with similarity in triangles. There were four for congruence on triangles, only three for similarity. And this one should sound familiar to you as well. Side angle side similarity theorem. This is a theorem because it is not common sense. You actually have to see the proof of it to understand that this is the way it does work. But you can take my word for it that it does work. Anyway, side angle side. This rule was also used for proving triangles to be congruent. But of course, with similarity, we're only worried about proportions, not congruence. Okay, so side angle side says that if two sides of one triangle are proportional to two sides of a second triangle, and the included angles, meaning the angles that are between those two sets of sides, are congruent, then the triangles are similar. Okay, so please pay attention to the positioning of the angles. It even says it in the name, side, then angles, then another set of sides. Okay, so obviously, we would be thinking about possibly utilizing the side angle side similarity theorem if maybe we had kind of mixed and matched information about the triangle, some of the sides, some of the angles, but maybe not all of the sides or all of the angles. Then maybe side angle side can come to your rescue. Okay, now obviously you got some side information going on inside of your triangles if you're thinking about side angle side. So we are going to have to set up a proportion, okay, but it actually isn't as bad as side, 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 because in this case we only have two sets of sides. That means we're only going to have one proportion, okay? But if that proportion does turn out to be true, and the angles in between the sides that that proportion is working on are congruent, then you would be able to say, yes, triangle ABC is similar to triangle DEF, and the shortcut would be by side angle side. Now, just like with the congruence postulates, folks, if you're trying to use one of the shortcuts and you do not list the shortcut that you are using, then you are establishing that you can prove that all of the angles are congruent as is required, and you can prove that all of the sets of side lengths are proportional as required. Okay, so if you don't list the shortcut, you got to be able to prove it all, and if you can't prove it all, then your answer is going to be wrong. Similarly, if you pick on one of the shortcuts and that's not actually the shortcut that works in the problem that you have, that would be another reason for you to be wrong. Okay, So let's take a look at these problems. Okay, what we've been doing, we've got these 5 different sets of triangles, and let's see if we can figure out if these triangles can be similar or not. Okay, we'll start off with the one at the upper left. Okay, so as you're copying it down, let's start talking about it. Obviously, we do not have any side length information at all. Okay, so that is going to take out side, side, side. It's also going to take out side, angle, side. Our only hope is the angle, angle similarity postulate. So the angle, angle says you need to have 2 sets of angles congruent. Well, let's take a look. Well, first off, these 2 angles right there. Those are vertical angles. They're across from each other at the intersection, and by definition, vertical angles are always congruent. So there is 1 set of congruent angles. Now, please notice on this one also, you have parallel lines, and our parallel lines are being connected by other line segments. That would be a transversal. Okay, so if we were to look and say, all right, I've got 2 lines that are parallel, there and there. They are connected by a transversal. So what kind of angles does that make? Maybe like those 2 guys. Those would be alternate interior angles. And the rule for alternate interior angles says if your lines are parallel, then your alternate interior angles are always congruent to each other. So we do indeed have enough information to say, yes, these triangles are congruent by angle, angle. Okay, let's go all the way to the right side of the page. Looks like my 4 is a little bit out of place. It should be sitting over here. Okay, but let's see if we have enough information to prove that these guys are going to be similar. All right, obviously we do not have any angle information, nor do we seem to have a way of finding any of the angle information. So that's going to leave us solely with the side, side, side similarity theorem. Okay, so we're going to need to check and see if these proportions controlling these triangles is going to be true or not. Okay, so I'm going to set up a proportion. Okay, and we'll see if it's true, and then we'll decide if we want to go any further. Okay, so I'm going to pick the smallest value from the triangle on the left. That would be the 4, and it should correspond to the smallest value from the triangle on the right. That would be the 1. Okay, so I'm coming back to the left. The next biggest side would be the 5, and on the right, the next biggest side would be the 2. Okay, so this would be one of the proportions that would need to work. Let's check it and see. Okay, 4 times 2 is 8. That needs to equal 5 times 1, which is 5. Does 8 equal 5? 8 does not equal 5. This proportion is not true. Okay, what that means is we do not have any angle information, and the side information is not working out. So we would be forced to say that these triangles are not similar. Okay, moving to the triangles in the middle. Okay, let's see what we have here. We have 1 set of side information. Okay, we have the side that's being shared between the 2 triangles there. Okay, we don't have a measurement to go along with that, but if push came to shove, we could say, you know what, whatever measurement this guy is, if it was X, then in the other triangle it would also be X. But that doesn't help us a lot as far as trying to plug into a proportion to find out if they're similar. Okay, so that's not helpful. We can look for some angle information. If we knew that these side lengths were parallel in the triangle, then that would allow us to use the rules of our transversal or alternate interior angles, stuff like that. But we don't know if these lines are parallel or not. Okay, so I don't see any way that we can come up with any other side information. We don't have right triangles, so we don't know if Pythagorean theorem would work. I don't see any way to come up with any other angle information, since we don't know if we have any parallel lines or anything like that. So I believe in this case, we would be forced to say no. Okay, and it may be that they are similar, but based upon the information we have, we simply do not have enough to determine that. Okay, now moving to the triangles down on the left side, obviously, once again, We have all kinds of side information, but we do not have any angle information. So that means we're probably going to be looking at side, side, side to see if this will work or not. So let's set up some proportions here. Okay, on the left side, the smallest side length would be the 2. The largest or the smallest side length on the right would be the 1. Coming back to the left, next smallest would be the 4. And on the right, the next smallest would be the 2. Okay, we cross multiply that and see if it checks out. 2 times 2 is 4. Does that equal 4 times 1, which is 4? It does work. Okay, so that's one proportion down. Now we need another one. 4 is to 2 as, okay, now I've got the medium side lengths. I would compare those to the large side lengths. That would be the 5 and the 2.5. Let's check that. 4 times 2.5 is 10. That needs to equal 5 times 2, which is also 10. That one works. So 2 of the proportions are working. That means we have one more proportion to check. Okay, I'm going to take the large side lengths, which was the 5 and the 2.5, and compare them back to the smallest side lengths, which was the original ratio, 2 to 1. Let's cross multiply and check that. 5 times 1 is 5. 2 times 2.5 is also 5. All three proportions are working. That would allow us to say, yes, these triangles are similar by side, side, side similarity theorem. Okay, so it took a little work to get that one, but there it is. And lastly, down at the bottom right, okay, we have one set of angles marked as right angles, so we definitely have one set of angles congruent, and we have information about two sets of sides, so we should be thinking about side, side, side. But we need to check these sides to see if they are in proportion, so let's check it out. Set up a proportion. I'm going to get the small side out of the top triangle. That would be the 5, which would match up to the small side of the bottom triangle. That's the 2. And the large side that we know, 22. Oops, messed that up. 22.5. And the larger one on the right, or the bottom rather, would be the 9. Cross multiply 5 times 9 is 45, and the question is, does that equal 2 of the 22.5, which is also 45. So what we have is we have two sets of sides that are proportional, and the angles between those two sets of sides are congruent. So we can say yes by side, angle, side. Okay, so once again, just like with congruency, it's all about evaluating what the problem has and comparing that to the rules that we do have to see if one of them will match up or not. I appreciate you finding time to do your notes. I will see you in class on Thursday.